heteroscedasticity test, laser test, etc. So we just give you some outline of this Bruce Godfrey test. First of all, I have fit this. You see that this is n variable regression line. Okay, y is equal to alpha plus beta 1 x1 I, beta 2 x2 etc. ui. Here we assume that variance of ui, that is sigma I square. This implies that obviously the variance of ui varies over the values of I. As xi values take some larger ones, this variance obviously becomes different. That's why this is sigma I square. And it is a function of several independent variables like z1, z2, zr. Sometimes these zr values are taken equal to the x values, and it is usually important to assume that ultimately these zr values are taken to be equivalent to xi values. But it might be difficult to understand this here. First of all, what is the hypothesis here? Before we set the hypothesis, we see that instead of sigma square, I take ei square, because ei square is some sort of substitute value for sigma square. This is again fit to be gamma 0 plus gamma 1 z1 I, gamma 2 z2 I up to gamma r z1 I plus vi. That means if there is a function of this entire stretch, that is taken to be same here ei square. And hypothesis is that gamma 1, gamma 2 up to gamma r are all zeros. If at least one of the gammas are non-zero, then we have heteroscedasticity. Why it is so? If at least one of the gammas are non-zero, then we have heteroscedasticity, because in that case, sigma I square, that is variance of ui, would be dependent on this zi term. If at least one of the gamma is non-zero, suppose gamma 2 is non-zero, then ei square is equal to gamma 2 z2. That is dependent on zy, and it is important that when we actually estimate this by employing abuse software, it is usually the convention to equate these z values with x values. So it is not very difficult to find this by applying abuse software. And after applying this in this software, you will find some ln statistic, which is actually n into r square, where r square is the given value in the regression output r square, and lm is equal to n into r square. Lm means Lagrange multiplier. Lm statistics or Lagrange multiplier, which is equivalent to n into r square. This follows chi-square distribution with r degrees of freedom. If lm is greater than, this is not coming here, this is actually chi-square, some alpha with degrees of freedom are right here, then high heteroscedasticity is detected. That means you nullify this hypothesis. You reject this null hypothesis. If this is greater than this tabular value, then you reject the null hypothesis and accept that there is heteroscedasticity. I give an example again. I copy this. When I'm copying these things, you start from these headlines: carbon, GNIPC, lit. Copy up to the last stretch of the values. How many values are there?
90.
90. 91 actually this way. The first row does carbon GNP, so 90 values altogether. So I have copied it. Come to this software. File, new, work file. Then unstructured unrated, put here, how much? 90. Then quick, then empty group. Install this here. Sorry. Wrongly. This. Let's go. Put 90. It's making a problem. The data has come here. After a long effort, it has come. There is some problem. Then what should you do? What should you do? You regress one variable on the other two here. After regressing, you want to test the presence of heteroscedasticity. Suppose this carbon is dependent on GNIPC and literacy. Make equation. So it is written carbon, GNIPC, lit, literacy and C. C stands for constant. So this is the result. Now you want to check whether there is heteroscedasticity problem here or not. There are several tests for checking heteroscedasticity. One is Goldfeld-Bond test, Glaser test, White test, Bush-Godfrey test. You see, I click here, view, then residual diagnostics. And you see that below here, we have heteroscedasticity tests. Okay. Then dialog box opens here. And you see that there are several things, Glaser, White, Bruce, Godfrey, Pagan, etc. Usually, the well-known tests are Bruce, Pagan, Godfrey, Glaser, and White. Amongst these three, White is the most well-known test of heteroscedasticity. So I start with White. Okay. Gives you the result. Behaving unpredictably, randomly. Once more, let me change. It's very bad. Result is somebody of you came later, so I start again here. Try to see this. This is behaving unpredictably. So I copy this data. It's not allowing me to copy this data. Okay, copy it. So copy it has been successful, I think. Then this is the eView software. Make equation. Right. There is also a problem. Next, what is the step? I told you to find out these tests. You go to view. Remember the steps. Go to view. Then residual diagnostics. Here from you come here, heteroscedastic tests. Then say white. You have these results. Now, how to check whether there is heteroscedasticity or not from these results? You see that on top we have observation multiplied by r squared. The second row, observations, number of observations multiplied by r squared. That is r squared. That is n into r squared. Number of observations, that is n, multiplied by r squared. That value is given here. And its probability is on the rightmost side, that is 0.003. If probability is very small, I already told you that if it lies between 0 to 0.10, then that is significant. That means this particular statistic, Lagrange multiplier test statistic, is significant. And if it is significant, then we can assume that there is significant level of heteroscedasticity in the given data. Understood? You refer to the second row, observation multiply, the star means multiply by r square. That value is 23.00 and that probability is 0.0003. That means it is significant. The probability lies between 0 to 0.10. It is significant, and that means the LM statistic is significant. LM is equal to n into r square. And since significant, we assume that there is not homoscedasticity, there is unequal variance, that is heteroscedasticity is present. And if one particular test establishes that there is heteroscedasticity, then all the other possible tests also should do the same. That means Glaser test as well as Bush-Godfrey test should also establish that similar kind of result, that is heteroscedasticity, should be established on the basis of this given data. And you can carry on this yourself. You do not have computer here. And this particular laptop is behaving unpredictably. Virus. Let me check once. So this has come result. Let me use another test. How to do that? First of all, you run the regression of what? Carbon on the other variables, including the constant. You see that we have C here constant, LIT, that is literacy, as well as GNIPC. What is that? Gross national income per capita. GNIPC, gross national income per capita. It is assumed that as gross national income per capita increases, this carbon emission should also increase in the economy. On the basis of environmental economics, we can assume this. As literacy level rises, we can assume that people may be more concerned about the environment and they may reduce the emission of carbon. Okay. Or reverse also may be. Sometimes the expected signs may be on either way. It might be positive, it might be negative. The more the literate person, the more they use their cars. Instead of being conscious about the atmosphere or climate, they can use more cars, and in that sense, carbon emission might rise. Here we are seeing that literacy has positive sign. That means people are using more cars as they are becoming more literate. They are accustomed to using more cars, having good services, jobs, and they are accustomed to using good cars. And you tell me whether this regression is significant or not. Whether R-square is good, whether individual coefficients are significant, etc. Tell me from this result. Tell me from the center result whether R-square is significant, whether individual coefficients are significant. First of all, that should be settled down. What about R-square? If you that a statistic, R-square is there 0.63. The test for R-square is F statistic. The test for R-square is done by F statistic. F statistics probability is 0.00. That means R-square is significant. This is simple. And now tell me which of the variables, individual expanded variables, are significant and which are not. Or all are significant or all are insignificant. On the basis of this data. For finding the significance level, you refer to the probability. Tell me. Which one? GNIPC is significant because it's probability. You refer to the probability first on the rightmost corner. So 0.00 is very highly significant, and the literacy non-significant. This is 0.75, beyond 0.10, highly beyond 0.10. So one variable is significant, another variable is insignificant, but the R-square is very much significant. Therefore, this regression can be accepted. Regression is significant. Once this is established, now you carry on the heteroscedasticity test by using some test which is other than white. Suppose, where to click now? View. So click view here. Then residual diagnostics. Then heteroscedasticity tests. Then we have Bruce Godfrey pattern, which is automatically selected. Default basis. Click here. Now tell me whether heteroscedasticity here on the basis of LM statistic. LM means observation into R-square. Tell me. It's significant. 0.00. The first value, that is white, on the basis of white's test, we found that value, observation multiplied by R-square was 23. Here it is 21. 23 point something, it is 21 point something, and it is still significant because probability is 0.00%. That's 0. That means whatever result has been established by White's test is also ratified by this Bush-Godfrey test. Same result, same kind of result. And similarly, Glaser test also should establish the same kind of result. Once you find this heteroscedasticity, existence of heteroscedasticity, then you try to erase this heteroscedasticity by means of this, applying this thing, the earlier one, by making the error term free from heteroscedastic problem, making it homoscedastic, then apply OLS method. Then the results will be correct. Otherwise, you take it from me, whenever heteroscedasticity is found to be significant, it is present in significant form, and still you apply OLS, you continue to apply OLS, your results will be not efficient. Your results, that is estimated parameters, they will be unbiased and consistent, but they will be inefficient. They will not have any more minimum variance. Therefore, you must have to rectify this heteroscedasticity by means of some sort of conversion of this model. So this is about this heteroscedasticity. This particular complex taking a lot of time. Have you heard this topic? Name multicollinearity. What is this multicollinearity? This multicollinearity problem is relevant when we have more than one explanatory variable on the right hand side of the regression. Repeating this multicollinearity problem arises when we have more than one explanatory variable on the right hand side. That means if you consider yi is equal to alpha plus beta 2 xi, beta xi, alpha plus beta xi. In that case, there will be no multicollinearity because only one independent variable has been assumed on the right hand side. But if you assume the regression like this, yi is equal to alpha plus beta 1 x1i plus beta 2 x2i, that plus ui, that means more than one explanatory variable has been assumed on the right hand side. In that case, there is the possibility of multicollinearity. What is multicollinearity?
Can we say that more independent variables are affecting the dependent variable?
Indirectly, you can say that when more than one independent variable are affecting or are influencing the dependent variable, there is the chance of multicollinearity. More than one. Multicollinearity rises when the explanatory variables are themselves correlated. If x1 and x2 are correlated, then there is the chance of multicollinearity. And that also makes your coefficients inefficient. Exact linear relation, you see that I have assumed one exact linear relation. Lambda 1 x1 plus lambda 2 x2 plus lambda k xk is equal to 0. That means all these xk variables, x1 to xk, these are related in a linear fashion, such that if you multiply each of the variables by some coefficient and sum them up, they will be equal to 0. That means, in other words, you can express either of the variable as function of the other variables, isn't it? If you take lambda k xk on this side, right? If you keep lambda k xk on this left hand side and you shift all these variables on the right hand side, this will all be negative of this. Negative lambda 1 x1, negative lambda 2 x2 and so on. Then finally, if you divide this right hand side by lambda k, that means xk is a function of all these variables. Xk is a function of variables x1 to xk minus 1. Linear function. If it is so, then there is perfect multicollinearity. That means one of the variables is a function of other variables. Now take simple case, two variables, not a variables, two variables. If you take two variables, what will be? This will be like this. Lambda 1 x1 plus lambda 2 x2 is equal to 0, isn't it? Take two variables instead of k. Then what will happen? x2 is equal to minus lambda 1 x1 by lambda 2. Isn't it? What is lambda 1, lambda 2? These are coefficients. I can write this in this from some minus theta into x1. This is theta, lambda 1 by lambda 2. Some other constant or parameter. So x2 is a linear function of this x1 minus theta x1. If this sort of exact linear relationship holds good in case of the expanded variables in a model, then we have perfect multi-quadratic problem, and that will destabilize your estimations. How does it done? You take this example, numerical example. What is the relation here between x3 and x2? You see that for all these values, x3 is 5 times x2, isn't it? x3 is 5 times x2. x2 and x4 are highly correlated. They are not exactly correlated, but maybe correlated. But x3 and x2 are highly correlated. Highly correlated because one is just multiplied by something. 5 multiplied by x2, that gives you x3. Exact linear relationship. But here we have 5 into 10 plus 2. 5 into 1575, it is exact, but not for all the variables. This is 5 into 80 plus 7. So it is near exact, not exact. Sometimes it is matching, sometimes it is not matching. Sometimes some variables have to be added or subtracted. 5 into 1, 24, that is 120 plus 9. 5 into 30, 150 plus 2. So this is called near exact multiplication, highly correlated. And in this case, the correlation coefficient might be so for x2 and x4. But for this, what will be the correlation? You know, without calculating the correlation coefficient between x3 and x2, I can tell you what is the correlation. When the variables are exactly linearly correlated, the correlation will be either positive or negative 1. Here it is positive, so it is 1. Exact linear relation between two variables, there will be positive 1. Without calculating correlation coefficient, I can tell
It is a scale of -1 to 1.
Correlation coefficient lying between -1 to +1. Range. That is range. It can be proved also. In multiple regression equation, when we have only two variables on the right hand side, the estimates beta 1 hat, beta 2 hat will be like this. I have given these things earlier also. In case of perfect multicollinearity, R12, hence R12 square would be 1. What is R12? That is correlation between x1 and x2. In case of perfect multicollinearity, correlation between x1 and x2 will be 1. That is R is equal to 1, R squared is also 1. Right? You must know that why I have written R squared positive 1. In case of perfect multicollinearity, R may be -1 or +1. It might be negatively related. In this example, this is negatively related. Exactly negatively related. So in this case, correlation between x1 and x2 will be -1. Without calculating it, I can take -1. Had it been plus theta x1, it will be plus x, the correlation will be +1, and in any case R square will be +1. R may be -1 or R may be +1, R square will also be positive. it is not possible to compute the value of OLS estimates. OLS technique breaks down in case of multiplicativity. Imperfect multiplicativity is where R square is less than 1. Variance of beta 1 hat, variance of beta 2 hat. The formula for this is this in case of 3 variable regression model. And you see that if R12 square is 1, that means there is perfect linear relation between two variables on the right hand side. Then that means this is 1 minus 1 0. Something by 0 is infinity. Here also something by 0 is infinity. That means variance of beta 1 hat, variance of beta 2 hat is really imprecise, not precisely estimated. We cannot precisely estimate what is the variance of these estimators when there is perfect multiplicity between any two variables considered. And high value of R square makes variance of coefficient very large. If this is not exactly 1, it is very near to 1, then what will happen? This variance will be very large. Why? If it is very large, then 1 minus this very large value will be very small, isn't it? Suppose this is 0.99, 1 minus 0.9 very small, 0.01. Something divided by some smaller thing very large, mathematically. So very large variance is not good. We always want to minimize the variance. If you consider the last class lecture, Professor Chakrabarty has taken this variance class. So we want to minimize the variance always, because variance means the extent of spread of the values with respect to the mean value. Average spread. So first of all, variance, this is called variance inflating factor. The variance inflating factor is 1 by 1 minus R23 square. This point was there. Here we have 1 by 1 minus R12 square. 1 by 1 minus R12 square. This is the variance inflating factor. This might be R23, this might be R12, etc. Depending on which variable are on the right hand side. I consider that on the right hand side I have taken say variables in the name of x2 and x3. It doesn't matter. I could have written on the basis of this 1 by 1 minus R12 square. Suppose I have taken the other names x2 and x3. That's why I have written 1 by 1 minus R2 square. Variance of beta hat is equal to this anyway. This will be like this variance inflating factor multiplied by variance inflating factor. This is the common term for both these values. If the variance inflating factor is greater than 10, then you suspect multiplicity. Usually, conventional value. If the variance inflating factor value is greater than 10 on the basis of your EPU software, then you suspect multiplicity. I will show you by means of some software, this EPU software, by taking one example. Remedial measures of multiplicity. How can I check this multiplicity? As you told me that the more the number of variables on the right hand side, the more the probability or possibility of the emergence of multiplicity, isn't it? More the variables on the right hand side, y is equal to function of x1 up to xk on the right hand side. So it is possible that at least either of these k variables, either two of these k variables may be highly correlated. There is a great possibility. The lower the number of variables on the right hand side, the lower the probability of multiplicity. So I start with the last one, dropping variables. If there are too many variables on the right hand side, and you try to drop some variables, then the possibility of the emergence of multiplicity is lessened, lowered. Huh? see,
How can we decide?
dropping means you do not consider them in the model itself. Instead of considering k variables, you consider say r variables, less than k variables. Okay. Suppose there are 5 variables. Instead of 5, you consider 3 variables. If you reduce the number of variables, the chances of
There are
multiple.
5 variables and we are considering 3 variables. Which 3 variables?
That means which variables, that is the problem. Right. Okay. So big one as well as beta 1 x1 plus beta 2 x2 plus beta 3 x3 beta 4 x4 plus beta 5 x5 plus q is also multiple regression. How many variables on the right hand side? Tell me. Right hand side of what image? Expanded variables. Right hand side I have only expanded variables, which is called as regressors. Alternative name is regressor. On the left hand side I have explained variable. These are explanatory, this is explained. And this explained variable is also termed as regressant. Alternative names these are. Regressor, regressant, explanatory, explained. How many explanatory variables or regressors on the right hand side? 5. x1 to x5. Now if you drop 2 variables, say, or 3 variables, chances would be greater that multiplicative would be lessened. Question is, which variables should be dropped? For that purpose, you find out the correlation matrix of these variables. And if you find that correlation, 2 variable correlation, pairwise correlation in some of the cases is very high, then you drop them. I can check it by using software. Understood? I am showing it to you. Before that, I want to finish this. Remedial measures of multiplicative. Increasing sample size. If you increase the sample size, then we can reduce the probability of multiplicative. How? You see that if you increase the sample size, then this summation xi squared, summation x1 and summation x2 squared, this summation value of x1 square, etc., would it be small or large if you increase the number of samples? Whether this summation x1 I square multiplied by this summation x2 square multiplied by this, these values will be larger or smaller when you increase the samples. Larger, because you are taking more of this I values. In earlier case, probably it was 1 to k, now you are taking 1 to n, where n is greater than k. If this is larger, then this is divided by some larger value, then this will be smaller. Isn't it? This will be smaller, and variance of beta will be smaller, and our purpose is to reduce the variance, and our purpose is to dimension sort. We can check this multiplicative by reducing the variance of this estimators. Transformation of variables. How this is done? Probably there is multiplicative. Instead of taking this individual yi values, if you take log values, log of yi, log of x1, log of x2, log of x3, etc., then it might be so that log values may not be so much correlated, because these are not in the proper linear scale. Since linear scale is not there, ratio scale comes into factor, so the chances of multiplicative will be reduced. So transform the variables by taking logarithms. Okay. And using some extraneous information, it is not so much important. Now I come to this. Same data I am copying. Remember these steps, unstructured or unrated, then this is how many? 90. The same data set. Then quick, go to empty group, bring this here, the data. Again the correlation. Why this? Software problems. Let me try with my own copied software. Just one. The data has been copied. From quickly, here again, you come to group statistics. From group statistics, you see that there is correlations. Okay. You list the variables. What are the names of the variables? Capital letter CARBON. Always give some one space between the consecutive words. Then GNIEC. Exact letter should be copied. One gap within the letters, between the letters. Okay. Problem there is. This should have come. The pirated softwares. Let me check once more this. Then quick group statistics, correlations. Copy this. Yeah. Let me check what happens. Correlation comes. Correlation has come. Tell me the correlation. What about the correlation? Pairwise correlation. Can you interpret this correlation table?
Yes.
When the variables are same, the correlation is 1. Similar variable. X1, sorry, carbon 1, GNIPC. That means along the principal diagonal we have 1 variables. And up principal diagonals we have some data which is less than 1. Which of the variables supposed to be highly correlated? You see that somewhere I find correlation value is 0.79. Somewhere I find correlation is 0.53, somewhere 0.43. So 0.79 is the highest among these three values. But still 0.79 is somewhat less than 1. Maximum value of correlation is 1. It is sufficiently less than 1. It is on the higher side, but it is not exactly 1. It it is sufficiently less than 1.79. So you must know that multiplicity is always to some extent present. That is called imperfect multiplicity. You cannot free any model from imperfect multiplicity. The data are always suffering from imperfect multiplicity. The problem will be high when there is perfect multiplicity. So even if there is moderate degree of imperfect multiplicity, you can carry on your calculations. That is allowable. So here, on the basis of the observations, I find that there is some degree of multiplicity, of course, but that is imperfect multiplicity. But if you are skeptic, you can obviously what should you do? If you are very much skeptic, 0.79. That is carbon and GNIPC. But you say that carbon and GNIPC, carbon is the dependent variable. The problem is between independent variables. Check what are the independent variables in this model. When I wrote the regression here, I wrote carbon first, remember? Carbon. Then the other variables. And I am taking actually carbon to be dependent, the other variables to be independent. What are the other variables? GNIPC and LIT. What is the degree of correlation between these two, GNIPC and LIT, from here? 0.53. So that is very moderate. So it implies that you are free to carry on the calculations. Had at least one of the correlations between two of the explanatory variables been closer to 1, you should have dropped those two variables. That is our solution. The more the number of variables, the more the multiplicity. And I can check it some other. I have some extended data set. There is, you see that there is less degree of multiplicity because the correlation between the two explanatory variables is 1.53. So you are free to continue the calculations. What calculation? You replace carbon on GNIPC and LIT. So how to replace? Make equation, and this is already written. Carbon is the dependent variable, first variable is dependent, the other variables are independent, including this C. C means constant. This is the regression result. Now interpret this regression result. And tell me what is the result of this regression. I think from this lecture, you can have some idea about how to interpret it, because I am concentrating on these things only. Not many things have been covered. GNIPC is significant, probability is very high, 0. Had it been 0.10, you should have considered significant. This is not significant. We do not bother about this. Generally, we do not bother about constant. What about R square? R square is 0.63. F statistic is significant, very high significant. So you accept this regression. It's a good fit. And you see that multiplicity has not done great damage to your calculations. Had multiplicity done damage to your calculations, then this would have been very high. Neither of this would have been significant. So that is the convention. Okay. So this is, in short, about the concept of multiplicity, how to detect it and how to establish its problem. For this purpose, I refer you to the book by Gujarati. Another book I will refer to you, which has extensive coverage of EBUs, that is by Shankar Kumar Bhumik. Our friend Shankar Kumar Bhumik, previously from Calcutta University, he has written a good book on econometrics by using software that is quite easily understandable. You can also purchase it 750 around the rupees. Econometrics using basic econometrics like this using EBUs by Oxford University. Anybody interested in using econometrics by using EBUs in further calculations, it is very easy to understand. So I have covered how many things? Regression, two variable, multiple variable, heteroscedasticity, multi-quantity. There is another problem which is known as autocorrelation in econometrics. I will not do much exercise on it. There is one test for autocorrelation which is known as Darwin-Watson test, which is the most acceptable test for detecting the presence of autocorrelation, and this is given in this result also. You see, you see that in this result we have Darwin-Watson statistic value. Last, how to check by finding this Darwin-Watson value whether there is autocorrelation or not. The presence of autocorrelation also destabilizes your estimators. It should be autocorrelation free. D is actually equal to 2 into 1 minus rho hat. D means Darwin-Watson statistic. 2 into 1 minus rho hat means the degree of autocorrelation between the serial values of the residuals. If the residuals, that is EI values residuals, are serially correlated, then there is autocorrelation. So take it from me that if this D value is either 0 or 4, then what happens? Rho hat is the presence of autocorrelation. Rho hat. This value can take -1 to +1 value. This rho hat. There is also correlation some sort. If D is 0, then what happens? This is how much? 1. If D is 0, that means rho hat is equal to 1. Rho hat is equal to 1. If rho hat is equal to -1, then D is equal to 4. So this is -1. Rho hat lies between -1 to +1, like simple correlation coefficient. This is called serial correlation between the residuals. And we want to avoid this. And if rho hat is equal to 0, then D is equal to 2. D is equal to 2 if rho hat is equal to 0, isn't it? So from this value we can check that if D value is lying somewhere near 0 or somewhere near 4, there is high degree of autocorrelation. If it is near the value of 2, there is no autocorrelation. Now check and tell you from the Darwin-Watson. Darwin-Watson test statistic, that is D. It is 1.89. What will you define? No odd presence. Sometimes it is not exactly 2, not exactly 0, not exactly 4 also. But it is near, it is hovering near. And on that basis, you should have to exercise your own rational behavior. If it is 1.89, it is nearing 2, that means rho hat is equal to 0, isn't it? We can interpret it like this. If it is nearing to 2, it is almost 0 or something less than 0, something. That means very little degree of autocorrelation. So we can accept this result without any further extra calculation. So this result is acceptable. This is free-form autocorrelation. We can see this. So this is one more problem. So how many problems we have understood? We have learned in this simple or extended regression model. How many? Tell me. Series by series, I am increasing the problems. First of all, started with heteroscedasticity, then multicollinearity, then autocorrelation. These two are really culprits of estimation. If all these three are there, all these culprits, you cannot estimate. But fortunately, at least either of these may be present, and you can assume you can do away with this by using generalized least square technique, which is beyond my scope to use here because.
So what is serial correlation? You are saying that autocorrelation is a serial when there is
serial
correlation.
dependence between the between successive residuals, EI values.
So EI values
Suppose
first I
E-
think E1, E2, E3 like this.
Like this. Serial means time series. Autocorrelation comes in time series. E of EIT plus 1 is non-zero. EIT plus 1 is non-zero. That means there is serial correlation in residuals. Serial means over the time series. T and T plus 1 are such.
Okay.
T plus 1, T plus 2.
Okay, time series.
Time series. It is a problem of time series. If you read the books by Damodar Gujarati, that will be very important for you at the beginning stage. And with this, you can supplement the book by Shankar Bhumik for using e-views. So we have learned three problems: heteroscedasticity, multicollinearity, and autocorrelation. And we have also learned how to check these things. Tell me how to check the existence of heteroscedasticity. We started in the second half class. What are the tests of the existence of the problems of heteroscedasticity? Heteroscedasticity. Pronounce it properly. Heteroscedasticity. HETEROSCEDASTICY.
When the basis of the error is not constant.
Now, what are the names of the tests?
Bruce.
Bruce Pagan. Right, Bruce Pagan. Then White. Another is Glaser. Goldfeld-Quant test is also there, but I'm not using all these things. I have not shown. White is most important among these three. You just take it. White's test. So we can use by using e-views. I will give you the steps for using these things. Here, I have written the steps for running this by using e-views. Multiple linear regression OLS, heteroscedasticity. What are the steps to be followed for using e-views? These are the steps. Bruce Pagan, Godfrey, Laser, White test, etc. Autocorrelation. You see that estimate model by applying OLS method. From the estimated result, click view, residual diagnostics, serial correlations, LM tests, open a small box for specifying the number of lags to be equal. Specify the number of lags. These by default chosen as 2, but can be changed as per our requirements. Click OK to obtain the output. This is the last case, when we detect autocorrelation and we can obviously avoid it. These are the steps. Multicollinearity. Obtain data in e-views Word file. Click view, then diagnostics correlation. Sixth box. Write the names of the variables in this box. Click OK to obtain the correlation matrix. Just we obtained earlier correlation matrix. On the basis of that, we have checked whether there is correlation or not. If you find that there is more than 2 variables or at least 2 variables which are highly linearly correlated, we can drop them. Otherwise, we can run the OLS regression. Variance inflating factor. How to find it? From the EVIEW's output window, click View, Coefficient Diagnostics, Variance Inflation Factor. You yourself can carry out these things well once you get these things, steps. Do you know panel data regression? Or this will be too heavy for you? Because we have 2 more hours to cover. Panel data regression. What is panel? Let me give you this story. Panel data means when cross-section and time series are crossing each other. Both are covered simultaneously. Suppose you have collected a number of data from a number of countries. Say the SAARC countries. SAARC countries covering Pakistan, India, Nepal, Sri Lanka, and Bangladesh, 5 countries. And you have covered the data for the last, say, 10 years. Then we have a time series of 10 years and cross-section of 5 countries. So how many data you will get in total? In total, how many data? Collected data. Cross-section, 5 countries, data for 10 years. 5 into 10, 50. Total number of data will be, size of data will be 50. And in this case, you can carry out your regression by either following fixed effect model or random effect model. Fixed effect model or random effect model. This is called, first of all, constant coefficient model. Before I discuss fixed effect model, I give you the concept of constant coefficient model. The CCM model, constant coefficient model, disregard the space and time dimension. This will be time dimension. Of panel data. In other words, even cross-sectional under CCM are assumed to be homogeneous, such that even cross-sectional units, it will be cross-sectional. Under CCM are assumed to be homogeneous, such that the value of intercept and slope coefficients are same irrespective of the cross-sectional unit, because the considered OLS is applied to estimate the parameters. Here, I do not want to give much time to explain this CCM model, because this is not often applied in reality. In reality, mostly applied is fixed effect or random effect model. But problem is the choice between these two. In which time we should apply the fixed effect model, in which case we should apply the random effect model. You should know the panel data can be divided into 2 types. One is called long panel, the other is called short panel. What is short panel? What is long panel? Long panel, when the number of time points is greater than the number of cross-section observations. Cross-section units. When the number of time points, T, say, capital T, is greater than the number of cross-section units, say N, that is called long panel. And what is short panel? When the number of time series units is less than the cross-sectional units, that is called short panel. And you must know that in case of short panel, when the number of cross-section units is larger than the number of time series units, the random matrix model is most relevant, and otherwise, vice versa. Limitations of fixed effect model. But before limitations, I give you this idea. Before telling you the limitations, I come to this idea. Suppose wage is a function of education of labor force. Wage depends on labor force. What is IT subscript? I stands for the individual number and T stands for the time point. You see that in the suffix of each of the variables on the right hand side and left hand side, we have two suffixes, I and T. So I stands for the individual, that is cross-section unit, T stands for the time series unit. So wage IT is a function of education IT. Here, what I have done actually. Male worker, female worker. Male worker's wage rate is assumed to be supposed to be higher compared to the female worker at the same level of education. Male worker's wage rate is generally assumed to be higher than the female worker's wage rate at the same level of education. This is realistically usually found. Then what will happen? We should fit two regression lines. One is for male worker on this upper side, and one is for female worker. And you see that if we extend this, we have the same slope, but the intercept will be what? Intercept will be different. It will be cutting here, it will be cutting here, with greater degree of intercept for the male workers. That implies that for the same degree of education, even with 0 degree of education, we have greater wage rate for the males compared to females, and for other education levels also. We have some differences. But if we had ignored this concept, if we had considered these points clustered in a single diagram, and we had fitted only one regression line, then perhaps this regression line would have been like this. Instead of like this, the same regression, single regression line possibly would have been negatively sloped, just deviating from this positive source. That is not desirable. Therefore, what do? We fit this model in this form. Had we fit only one regression line, it would have been like this. But this is not the essence of fixed effect model. Alpha IT plus beta education IT plus UIT. This is the model for fixed effect sense. Okay. What is alpha IT? This is the intercept term for the ith worker. Actually, I have taken here two workers. One is male, one is female. Alpha IT is the intercept term for the ith worker over time period. Okay, t time period, etc. And you see that this alpha this will be different for these two individuals, and if there have been n number of individuals, this will again have been different. But for each individual, this will have been same. For each individual, for each particular segment of population, these intercept would have been same. That's why it is said that for every particular segment of population, if it remains the same, then it is called fixed effect. Fixed effect. Okay. And this particular regression model has been reconsidered by applying dummy variables. That makes it a bit different. Alpha 1 d1t up to alpha n dnt plus beta a to it plus ut. You can raise one question. You say that beta is fixed here. Beta is also given here. Beta means the slope coefficient. The slope for these two lines remains the same. Isn't it? That's why beta remains the same on these two regression lines. Since beta measures the slope of these two regression lines, so beta is same. So beta, that's beta, there is no it here. This is varying. But this remains fixed for each segment of population. Here also it is varying. But it remains fixed for each segment of population. It is varying over this female worker and male worker when we have only two workers. Forget about this because I have considered dummy variable here. That makes it a bit more difficult. I have not told you dummy variable. That's why it may be difficult to make you understand this. Before I proceed further, I give you some outline about random effects model. It is further complicated. Intercept of ith cross-sectional units is expressed as, you see that alpha I is written as alpha 1 plus epsilon I. That is, intercept term has been composed of two terms. One is alpha 1, the other is epsilon I. This alpha 1 is purely without any I symbol. It is given. It is same for all individuals. This is varying. So this is the random term. Therefore, OHIT is equal to alpha I, that is alpha 1 plus epsilon I. Instead of writing alpha 1, we write alpha 1 plus, this is alpha 1, A1 plus A1. It should be A1. A1 is equal to alpha 1 plus epsilon I. So, alpha 1 plus epsilon I plus beta education IT plus IT. If you just take it. So this is alpha I. It's alright, not A. Alpha I is equal to alpha 1 plus epsilon I. Is alright. No problem. It is becoming very hazy. See. Now you see that we have some composite error term which is WIT. WIT is equal to UIT plus epsilon I. And we have these kind of things. WIT, WIS is correlated. And so on. In this case, what is the essence of this? Here we have considered the intercept parameter as composed of two things. One is random term, the other is fixed term. That is, alpha is equal to alpha 1 plus epsilon I. One is random, the other is given. For all the observations it is same, that is alpha 1. Since one term is random, it is called random effect model. Which one is random? That is epsilon I. And once you consider epsilon I have here we have some composite error term which is called WIT. WIT is equal to, what is WIT? UIT plus epsilon I. And because of this we have some problems here. In this case, in this sort of cases, we have random effects model. Now, question is when you apply random effect model, when you apply fixed effect model. In general, random effect model is considered suitable when the number of cross-section units is large. That I told you earlier. and the number of time series observation is small. In a short panel, number of cross-section units is greater than the number of time series points. Here RM becomes more appropriate. In case of longer panel means where the number of time points is greater than the number of cross-section units. In case of longer panel, number of time points exceeds the number of cross-section units. And in this case, fixed effect model becomes relevant. Choice between fixed effect and random effect is done by Houseman test. Houseman test. Limitations of fixed effect model. You just read these things, it is obvious. If you use too many dummy variables rather, the degrees of freedom, it cuts the degrees of freedom and becomes difficult to obtain precise estimates of unknown parameters. I'm coming to that. Intersection of many dummy variables varies the raises. Intersection of many dummy variables raises the possibility of multicollinearity. Precise estimates of unknown parameters may be difficult. The results of FEM are because of the assumption that E of EIT is normally distributed around zero mean and constant variance. Since I refers to cross-section units and T to the time series observations, the random term UIT is likely to suffer from heteroscedasticity and autocorrelation. In this case, these are the problems of fixed effect modeling, limitations. But often, in case of panel data, either knowingly or unknowingly, we use fixed effect or random effect model. How to check whether fixed effect model or random effect model will be more relevant? That is done by Houseman test. One checkpoint I have already told you. When the number of cross-section units is large than the time points, then it is very important, very relevant to use the random variable. I am reiterating. When you have short panel means when the number of cross-section units is larger than the number of time points, you rather opt for the random effect. And the first case you opt for the fixed effect. So this is one checking point. Because when you have access to the data, you can easily know what is the number of time points, what is the number of cross-sections, and therefore you choose from it. Another test is called Houseman test. That is econometric test. Now I try to show before you how this is done by using EView software, both of these models. Once more, I think I'll be in a software. See, we have panel data here. You see, this is the panel data. How to interpret this panel data? Poverty, RNFE, and LIT. These are the variables. Poverty depends on RNFE and DTIC. These are the statistical speculation of your model. Poverty depends on RNFE and DTIC. That is your model. So, dependent variable is poverty, RNFE, and LIT. These are the independent variables. And how do you know that this is a panel data? We see that these are the states. These states are there, the names of these states. And 1, 2, 3 stands for the time points. First year, second year, third year. It might be 2000, 2010, 2015, etc. So for each state, successively, for successive time points, I have written the data. And the time points are between 1 to 3. Instead of writing the exact years, I just write it 1, 2, 3, 1, 2, 3, etc. We have 17 states and 3 time points. So how many data? 51. Told you 3 multiplied by 17. So 51. Check it. 3 multiplied by 17, 51. But we have 52 here. That is because the first row gives you the variable names. So therefore, we have actually 51 data. Now copy it from this. How to make the copy? Including everything. State, year, poverty, this. So copy it. So copy it. For fixed effect, you have some other technique of putting these things here. You take balance panel. Balance panel. Then we have some other kind of dialog box. What is start date? 1. What is end date? 3. Number of cross sections? How many? 17. States cross section. I write poverty, RNFE, LIT, and C. The first variable is dependent variable. Then you go to panel options. Panel options, you take this. You see that there is fixed and random. Say you take fixed. Oh, in the data, what is there? Let me check what's the data. What is there? Results. Fixed effect. You see that cross sections in 17, total panel observations 51. That tallies with your ideas. Please consider ideas. So these are the variables which are taken on the right hand side. C, RNF, and IT. These are the expanded variables. Poverty has been regressed on this by the help of fixed effect model. Okay. In this case, simple ordinary least square technique has been used. Now, you just tell me what is the essence of this regression equation on the basis of the parameters probability sign and R square F statistics. Tell me. Which experimental variable is significant? LIT.
Yes, statistic.
No, first of all here,
C.
LIT is significant, RNF is also significant, isn't it? Probability is lying between 0 to 0.1. So you see that 0.04 is significant, 0.03 is also significant, gives you significant values of these two explanatory variables. What about R square? F statistics is highly significant. Say probability is 0, 0. If it is 0, 0, you just take it that it is highly significant. There is no other option. So this result on the basis of fixed effect model is highly encouraging. Now, just tell me, on the basis of the usual number of cross-section units, number of time series units, comparative aspect, which model should have been appropriate, more appropriate here? On the basis of number of time series units and cross-section units that I told you, long panel and short panel, on the basis of that particular statements, which particular model should have been more appropriate here? What did I tell you earlier? In case of short panel, in case of long panel, which are the more appropriate models? On that basis, what helps? Is it a long panel model or is it a short panel? First of all, why? Number of time points is less than the number of cross section. 3 is less than 70. In that case, which model is more appropriate? Cross-section units is larger compared to time series points. So random effect model would be more appropriate here. So sometimes fixed effect model, random effect model, both can be carried out. But it is ideal to give random effect model here, the results of random. Okay. So let us check whether random effect model can be. Then next step, what should be done? Balanced panel. So what is balanced panel? What is unbalanced panel? There are two things, balanced panel and unbalanced panel. Balanced panel means when the number of time series units for each cross-sectional unit is the same, then it is balanced panel. When the number of time series units for each cross-sectional unit is the same, then it is balanced panel. But when the number of time series points for each cross-sectional unit is not same, that is called unbalanced panel. Then on this basis of this definition, is it a balanced one or unbalanced? It is a balanced. For each cross-sectional unit, we have the same number of observations. What time series? 3 years. Then start date is 1. Then end date is 3. Cross section is 17. Okay. Then quick. You must click here quick. Then estimate equation. Write the equation format. Poverty R N F E then LIT then C. C is constant. Next step, what should I do? Panel option. we have both fixed and random. Yeah. So I have given random effect. This is not coming. So I have not done it now. And data has not been copied properly. Data was not there. Data was not copied, that's why there was problem. Now see that this is random effect result. I think the result is not correct. Some problem has occurred again. Where is virus retail authority? Now check it. This is the final result. Some error was coming. How could I detect that there was some problem? Virus attack. Yeah. Challenge problem. I'm checking. আমি মনে হচ্ছে কমপ্লিট ভাইরাস আছে হ্যাঁ হলেও কিন্তু বাংলাদেশে কোনো একটা প্রবলেম হচ্ছে তো পালিয়ে যাচ্ছে বা এটাতে স্কিপ করছে একবারে আসছে না এনিওয়ে now see that how can I detect that this is correct result method panel cross section random effects this is written on top of the result sheet and how this is more or less good fit compared to the earlier logic, fixed effect model. This is random. Try to interpret this result again. First of all, we concentrate on R square, also the individual significance of the coefficients. What about R square? R square is not shown, no? Full scale. Check. R square is how much? 0.16. 0.16. No? R square. 0.51. How much is R square? Tell me.
In percentage.
This is R square. What is statistics? You take weighted statistics, not unweighted. What about the probability? That is 0.00. What about the individual coefficients? There are if and it, whether they are significant or not. Again, you see probability level. It should not take much time. probability level, you see that it is less than 0.1, 0.05 and 0.01. So all the coefficients are significant, like the previous fixed effect model. R square is also significant. Therefore, both fixed effect and random effect model good fit here, but on the basis of the longer panel and shorter panel consideration, we take that this random effect model is most fit here, most good fit here. How to identify between these two? On this basis. Sometimes it might be so that the fixed effect model is not giving you good results, but random effect model is giving you good results. And sometimes the reverse way. In that case, you should consider the model which is giving you good results. But apart from this, whether for a particular data set, fixed effect model or random effect model will be applicable, that's why Houseman test is applied. Houseman test is a bit complicated. You see that Houseman test is coming. After carrying out the random effect model, you put on view, click on view, then comes fixed random effect testing. From this another box opens. You see that the last one is correlated random versus Houseman test that gives you the results of the test. Okay. How to check whether fixed effect or random effect will be applicable here? You see, chi-square statistic, how to identify it, whether fixed effect or random effect will be applicable on the basis of Houseman test. You concentrate here, chi-square statistic. What is the value? 1.5. What is the degrees of freedom? 2. What is the probability? 0.4688. Chi-square is also a test statistic. Probability is this. Then chi-square test statistic should be accepted or hypothesis should be accepted or not, because the chi-square value has the probability this. This is acceptance region, 0.488. Higher value, higher side. I told you, higher side is acceptance. Lower side is reaction, that is significant region. Acceptance means confidence region. Understood? Look at me, not to the T. So, acceptance is confidence region. Reaction is significance region. Here, this is very high, 0.48. So this is acceptance region. Null hypothesis is accepted, isn't it? When null hypothesis will be accepted, in that case, fixed effect model will not be applicable. Random effect model will be more relevant. That is the result. So on the basis of this test also, the random effect model comes to be relevant. Which I told you on the long panel and short panel basis, this is also verified on this. Now, short break, 10 minutes here. But we can carry out conversation here also. Or if you like to go, আমি এবার কোশ্চেন জিজ্ঞাসা করবো এরপরে আধ ঘন্টা ধরে আলোচনা করবো। ও রেজাল্ট দেখা যাচ্ছে না, তো বড় করে দিয়েছি, সামনে আসতে হবে, আগে বলতো স্ক্রিন তো আর বড় করা যাবে না, লং স্ক্রিন আছে, হাই স্ক্রিন আছে, কিন্তু আমাদের হাতে নেই। একটা ক্লাসে আমি অনেকগুলো কভার করেছি, up to panel data. It's not very easy job, but I have tried to make you understand in a very simple way. If you have these steps, I have given you steps, give you steps, After going home, you have access to use software, you practice it, and with this particular notes, you use as well as this PPT PowerPoint. So I think some improvement may be done. ঠিক আছে, সবাই যাচ্ছে। যদি মনে হয় যে কঠিন হয়ে যাচ্ছে, আমি অন্য কিছু চলে যাবো, লোয়ার ডিগ্রিতে চলে যাবো। আর এই কম্পিউটারটা অনেক টাইম নষ্ট করছে, যেটা মনে হচ্ছে কুইকলিটা আপডেট করা নিয়ে এরকম। কারণ আমার বাড়িতে আমি করি, খুব তাড়াতাড়ি কুইক হয়ে যাচ্ছে, তারপরে এইটা নড়ে হয়ে যাচ্ছে। You can go outside, right? Just sit here. নেক্সট ক্লাসে আমি অন্য কিছু চলে যাবো হালকা কিছু, ঠিক আছে? কালকে যেগুলো আলোচনা করা হচ্ছে সেগুলো আমি হ্যাঁ yesterday whatever was discussed in the class we can review that.
You'll be coming another day, sir? No, this is
Only today. So yesterday what was discussed? Kiki discussed.
Regression,
correlation.
Mean median mode.
mode.
Very easy. But for beginners that is also
Essential, sir. It's just essential.
essential to what? History people, some history people was there. Doesn't know anything. আপনার কি সাবজেক্ট?
Sir, I'm after education.
আপনার ম্যাডাম
I'm physical education.
কোথায়? কপি আছে তো আমার ছাত্র, কপি আছে না? আপনি কোথায় আছেন?
আচ্ছা, স্যার আপনার ছাত্রী?
হ্যাঁ, আমি পড়েছি, মেমেতে পড়েছি। আমার টিচিং এক্সপিরিয়েন্স হয়ে গেছে 33 ইয়ার্স, 85 থেকে পড়াচ্ছি, বহুদিন হয়ে গেছে। আমার যে প্রথম দিকে স্টুডেন্ট তাদের বয়স 50, আমার থেকে 7 বছর।
স্যার একটা কোশ্চেন আছে, পপুলেশন তো নরমালি ডিস্ট্রিবিউটেড হয়, কিছু ক্ষেত্রে আমরা যেগুলো ইনডিফাইনাইট সেগুলো আমরা বলতে পারি, কিন্তু যখন আমরা স্যাম্পল ড্র করছি এখান থেকে, তাহলে আমরা কি করে শিওর হব যে আওয়ার স্যাম্পল ইজ অলসো নরমালি ডিস্ট্রিবিউটেড?
পপুলেশনটা আমরা ধরে নিই নরমালি ডিস্ট্রিবিউটেড, এরকম নয় যে এটা ডিস্ট্রিবিউটেড আছে। পপুলেশন তো আমরা দেখতে পাচ্ছি না, আমরা ধরে নিচ্ছি নরমালি ডিস্ট্রিবিউটেড, ঠিক আছে? এবার স্যাম্পল থেকে, স্যাম্পল যে আমরা ড্র করছি, সেই স্যাম্পল থেকে যে স্ট্যাটিস্টিক গুলো হচ্ছে, স্ট্যাটিস্টিক স্যাম্পল, এই জিনিসগুলো আমি কিভাবে আলোচনা করবো, স্ট্যাটিস্টিক এন্ড প্যারামিটারস গুলো তফাৎ কি?
আরেকটা স্যার, if our sample is not normally distributed, then can we use parametric statistics to it?
And the non-parametric statistics, non-parametric test করতে হবে, non-parametric
But non-parametric is
test, এর অনেক কিছু আছে non-parametric, Wilcoxon test, man-Whitney test. যদি কারো স্ট্যাটিস্টিক্স এর ফার্স্ট হ্যান্ড নলেজ না থাকে, very difficult to understand this all these critical things. তবুও আমি যতটা পারি মেকানিক্যালি বলে দেওয়ার চেষ্টা করছি। একেবারে যাদের জিরো থেকে স্টার্ট করছে তাদের কিছুটা ইমপ্রুভমেন্ট হতে পারে। ইভিউ সফটওয়্যার ভেরি ইজি।
স্যার ইভিউ আর এসপিএসএস এর মধ্যে কোনটা?
এসপিএসএস ভালো, এসপিএসএস ভালো। এসপিএসএস একদিন দেখিয়েছি জন্য আমি দেখলাম।
আচ্ছা, হ্যাঁ
বাগলি দেখেছে না?
হ্যাঁ,
শুধু আমার স্টুডেন্ট।
হ্যাঁ হ্যাঁ,
বাগলি আর কবি তো হচ্ছে ওরা হাজবেন্ড ওয়াইফ। বাগলি আমার স্টুডেন্ট ছিল, তখন পেসিমিস্টিক।
তো এসপিএসটা নিয়ে সারাদিন লিখেছে।
হ্যাঁ আমি
এসপিএসটাই সারাদিন করে দিয়েছে।
কি কি দেখিয়েছি এসপিএস?
এসপিএসের বিভিন্ন ডেটা ছিল সেগুলো
মিডিয়াম মডেল
মানে ইম্পোর্ট করা ডেটা, তারপর কোরিলেশন।
এসপিএস এগুলো করা মুশকিল আছে, হাউসম্যান টেস্ট
হ্যাঁ
যেগুলো আর কমপ্লিকেটেড,
এগুলি ভিউসে
লজিক প্রবিট। লজিক প্রবিট আমি করালাম না, আমি ফিক্সড একটা জানি না। লজিক প্রবিট আমি ভেবেছিলাম করাবো, কিন্তু আর করাবো না, কারণ টাফ। তবে একটা কেস বলেছিল ডামি ডিপেন্ডেন্ট, ডামি ভেরিয়েবল, সেটা একটু হয়। পিএইচডি হয়ে গেছে
হচ্ছে স্যার
কিছু এডুকেশন রিলেটেড।
সাইকোলিঙ্গুইস্টিক্স।
তো কিছু এরকম সফটওয়্যার বেসড কিছু প্যাকেজ ইউজ করতে হবে নাকি রিগ্রেশন ডিপ্রেশন?
আমার বেসিক্যালি অ্যানোভা আছে, মিডিয়াম মোড নেই, টি টেস্টিং আছে।
একটা রিগ্রেশন করা তো
ভালো না?
it improves the quality of diseases. জোর করে করা উচিত না, কিন্তু যদি ডেটা থাকে তাহলে করতে পারবে। আর যদি ডেটা জোগাড় করতে পারা যায়, provided these things are taken care, heteroscedasticity, multiplicity এগুলো চেক করে যদি করতে পারা যায়, তাহলে it improves the quality of diseases. As if you have checked whether there is multiplicity, whether there is heteroscedasticity, or the goal is. অনেক সময় অটোপোলেশন থাকলে আস্কারের ভ্যালুটা খুব হাই হয়ে যায়, তখন ডার্বিনওয়াটসন টেস্টটা দেখতে হয় যে আস্কার ভ্যালু এত হাই হয়ে গেছে, দেয়ার ইজ সাম প্রবলেম সামওয়্যার। আমার একটা হয়েছিল, তখন আমি দেখেছিলাম যে ডার্বিনওয়াটসন ভ্যালুটা ওই যে বলেছিলাম 0, 4 আর 1 এই রেঞ্জের মধ্যে, তা দেখছিলাম ওটা ওদের 4 এর কাছাকাছি ছিল। 4 এর কাছাকাছি থাকলে কি হবে, মানে -1, রো ইজ ইকুয়াল টু -1, তার মানে there is high degree of autocorrelation. Therefore, we should not go into for the regression analysis. তখন সেখানে ওয়েটেড লিস্ট করে ইউজ করতে হবে। আপনাদের কলেজে পান আছে না, সকল পান প্রিন্সিপাল?
ডাইরেক্টলি আসেনি।
স্যার আপনার পরিচিত স্যার প্রিন্সিপাল স্যার?
কোন বাবু?
না, পান স্যার।
হ্যাঁ, ওয়েটেড মানে কপি করতে পারছি না কি হয় ওই পিপিটিটা হ্যাঁ আচ্ছা তারপর এই যে এটা আমি হচ্ছে দি এটা ক্লাস ফুলেট নেক্সট আসছে ফুল হ্যান্ড হচ্ছে कंट्रोल से देखो एकदम मोशन देखिए কিছু দেই হচ্ছে এটা নতুন দিয়ে যাবো তাহলে অন্য কোনো একটা ল্যাপটপে
হ্যালো, হ্যাঁ 2 মিনিট পর ফোন করছি, ঠিক 2 মিনিট পর। Rajiv, and I will give an responsibility. You will prepare 4 groups.
4 groups.
From all participants.
Okay.
Not break the mix-up group, not from the one area, not like that. Okay.
Random.
And okay, that group after on 9 first half writing research proposal, all things will be happen, and after that in the second half groups will prepare the research proposal and present. Okay, that's why
Ninth.
that's why I am asking to prepare 4 groups.
4 groups.
It's your responsibility.
To divide the total number by 4, then each group will get.
We have to prepare equal representation, male, area, bunch.
Means 4 to 5 will be there each group. And 5 from different department, and that will be miscellaneous.
So in the last day, our presentation, group's presentation will help us to clarify our doubts, and one person, resource person will be there. Dr. Tapas Chakravarti as the deputy, most probably deputy governor of Reserve Bank of India. So he will help in this regard, and he has a vast experience, and your presentation will help to generate a new look of your presentation, because we are preparing the research proposal just like in formats. Actually, recently formats are not appreciable, and based on your research design, it may just ऐसा सोचो कि हम लोग क्या करते हैं, पॉइंट्स वाइज लिख देते हैं, वो पॉइंट्स आपके रिसर्च में रेलेवेंस नहीं भी हो सकता है, फिर भी लिख देते हैं। इसलिए एक प्रैक्टिस सेशन जो छूट जाता है वो भी डाल सकते हैं, एक प्रैक्टिस भी हो जाएगा तो अच्छा रहेगा और नया आउटपुट होगा। इसीलिए आपको रिस्पॉन्सिबिलिटी दे रहे हैं कि आप 4 ग्रुप बनाओ, कल मुझे दे देना। ठीक है, দেখে দিন আমি তাতে 4:45 এ শেষ করতে হবে।
হ্যাঁ, এখন বেশি করে নাম নিন।
না না দেরি আমি করব না,
ওটা এক্সট্রা টাইম বাইরে থাকা
ওটা তো পার্টিসিপেন্টদের নিজের উচিত,
হ্যাঁ, সেটাই।
সেটা তো সবাই তো ন্যাচুরাল লোক, আমি তো আর দেখি
ঠিক
আমি খারাপ লাগে।
And then since when Sir said I was going to get some extra questions, and five people in one, and suppose 3 boys, 2 girls, the ratio should be equal. So the department also is 24. Equal to you will not get that, because we are in the same department. See?
Now we can start. We have learned the concept of correlation, simple correlation, that is product moment correlation, that is Pearson product moment correlation, that is covariance xy divided by sigma x into sigma. That is easy. Do you know there is another correlation coefficient that is known as rank correlation coefficient? Rank correlation. That is called Spearman's rank correlation. Product moment correlation is Pearson's correlation. Now, Spearman has given one concept is known as rank correlation. Rank correlation is applicable when there are two individuals. One individual is given some rank 1 to up to n. Another individual is also given rank 1 to n. But obviously the orderings may be different for each of the individuals. Why rankings comes into operation often? Suppose we are considering the level of intelligence and level of sales ability of a number of salesmen. Intelligence and sales ability or sales efficiency. Intelligence and sales efficiency of a number of salesmen. And you know that intelligence is not easily calculable or quantifiable. Similarly, sales ability, sales efficiency is also not easily quantifiable. In that case, what can we do? We can assign some rankings on the basis of their observed behavior. And the better intelligent person may be given highest rank or lowest rank in reverse ordering. But whatever you do, the ranking should be in the same order. I am telling you once more. Suppose we are interested in measuring rank correlation between two individuals. We are considering the intelligence and sales efficiency of a number of salesmen. Intelligence is not easily quantifiable. Sales efficiency is also not easily quantifiable. In that case, we can assign ranks to each of these individuals according to our intelligence and sales ability. Suppose the best salesman in terms of intelligence is assigned the rank 1, the worst is assigned the rank n when there are n individuals. In that case, the rank correlation coefficient formula is like this. RK stands for rank correlation sign symbol. This is called Spearman's rank correlation concept. 1 minus 6 sigma di square divided by a into n square minus 1, that is Spearman's rank correlation. What is di? Is xi minus yi. These are the ranks between the two series. Xi is the rank in one series, yi is the rank in another series. And both xi and yi can assume value 1 to n because there are n individuals. I'll give an example. The first individual is given rank 1, say, in terms of, this is suppose intelligence, sales efficiency. Suppose he is given 3. Suppose n is equal to 5 for the sake of simplicity of analysis. N is equal to 5. This is 3, second individual, this is 2. This is 4. This is 3. This is 2. This is 1. This is 5. This is 5. You could have raised one question. The same two individuals may be given the same rank. It might be so. Two individuals may be identical in terms of either sales or intelligence. In that case, it might be 3 also, or it might be 2, 4, it might be 4 also. This is the case of tied ranks, tied. But that makes the case rather complicated. I am considering here the case of untied ranks. There is no tie. And you see that when it is 1, it is 3, 3, 2, 4, 3, 2, 1, 5, 5. What is xi, yi? Xi minus yi, xi minus yi. What is this? Minus 2, 1, 1, minus 1. Now put the formula and get the rank. Easy. Sigma di square. Next you take di square, another column. Di square. So this will be 4, this will be 1, 1, 1. Okay. 4 di square, 1, 1, 1. All will be positive. Now take summation di square in the row, last row. Put the summation di square here. This is 6 sigma di square. This will be 5, 5 square minus 1. And again, rank correlation lies between minus 1 to plus 1. Anybody can check it. What will be the value? Check it. Very simple. And take that, and tell me the value. Whether it is exceeding 1 or less than minus 1. It will be lying between minus 1 to plus 1. Then definitely. Here consider xi to be intelligence, yi to be sales efficiency of 5 salesmen. Sigma di square is 7. 7. Six into 7 divided by n is 5. 5 square minus 1. You apply your calculator.
0.6.
0. Okay, it may be. So it is less than 1. When it will be 1, can you tell me? When it will be minus 1? Extreme cases. When the ranks are matching, in that case it will be 1. Because when the ranks are matching, sigma di square will be, what will be the value of sigma di square? 0. Because xi minus yi is 0. It is 1, it is also 1, it is 3, it is also 3 on either side. So sigma di square is equal to 0. So 1 minus 0, that is 1. When the ranks are totally unmatching, reverse order. 1, 5, 3, 4, 4, 3, and so on. And you can check, in that case it will be minus 1. Reverse order. So this is the simple case of rank correlation. I am not showing you the tied ranks. Yeah?
When the ranks are, if some of the ranks are equal, then how do we?
That is the case of tied ranks. Tied ranks.
So how do you proceed?
It's a very complicated one. You can see Engidar's book. Do you know Engidar's? So this is the formula in case of tied ranks. It's a very big formula. N square minus 1 divided by 12 minus kx plus ky summation minus summation di square divided by 12 divided by root over n square minus 1 divided by 12 minus tx into root over n square minus 1 divided by 12 minus ky, where tx is equal to k into k into k square. For the first series, x, the first series, T1, you can take I here. T1 is equal to kj square minus 1 divided by k. I don't exactly recollect, it might be 12n also, I'm not sure. I'm just missing the formula to some extent. It might be 12n or 12. You have to check it in Engineer's book or by Gungupta Dasgupta's first volume. There is a big formula, often not used, that's why it has gone out of my memory to some extent. It might be 12n or 12. What is this? This is the length of the tie in the first series. Ki stands for the length of the tie in the first series, length of the tie in the second series. And if there are more than one length of ties, in that case, this will be summation. This makes it more complicated.
Those more than 2 people will get 7.
Maybe. This is possible to apply when we have very good number of observations, not only 5. It is not restricted to 5. It is some 50, something like that. I am not discussing in detail, this makes it more complicated. I am giving you another example of finding rank correlation by applying Kendall's rank correlation concept, which is rather easy. Kendall's.
Data मेरा यहाँ पे नहीं दिया गलत से
These ranks are here. 1, 2, 3, etc. Suppose we give the ranks here 3, 4, 2, 5. The ranks are like this. Again, I have taken 5 individuals. 1, 3, 4, 2, 5, 3, 4, 2, 5, 1. Here you take pairwise ranks in both the series. Pairwise ranks. What do you do? This is one pair. The corresponding pair is there. If the pair of ranks in both the series are in the same order, then give value 1 to that pair. I reiterate. If the pair of ranks in both the series are in the same order, then assign value 1. Otherwise, negative 1. Positive 1. In the same order, reverse order, you assign negative 1. And in this way, count the possible number of values of ranks. First of all, you tell me how many possible pairs can be found out from here. 5 individuals. 5 individuals, how many pairs? 5C2. 2 is the pair. 2 individuals forming pair. Right. So 5C2 is the number of pairs. Number of possible pairs. Number of possible pairs is 5C2. What is 5C2?
15.
10. 5C2. 10. If all the pairs were in the same order, what is the maximum value can be given to this? 10 possible pairs are possible. So 5C2 is equal to 5C3, isn't it? 5C3 is equal to 5C2. So 5C3 by this. 5 into 4 into 3. Isn't it? This is actually factorial 2. This should be actually factorial 2. Factorial 2 and 2. 5C3. What is 5C3? 5C2. Same. How that can be found out? 5 into 4 into 3 into 3 into 1. No, if I apply this formula, 5 into 4 into 3, that is 4 into 5 is 20 into 3, 60. Divided by factorial 3, that is 6. So 60 by 6, that is 10. This is actually factorial 2. Factorial 2 means 2, that's why I'm not doing this 2. So 5C2 and 5C3 are same. Okay. Now the number of pairs possible is 10. So maximum value of these pairs in terms of Kendall sense, it is 1. That's 10. If all the pairs were in the same direction, each pair given the value of 1, then it will be maximum value of 10. Now here, what is the actual value that can be assigned here in Kendall sense? Consider this pair first. And here, these two individuals are in the same order or reverse order. 1, 3, 3, 4, increasing order. So assign this value 1 for this. Okay. In this way, you shall have to carry on your calculations for 10 pairs. Because maximum 10 pairs are there. 1 and 4. Consider this 1, 4, 3, 2. Another pair.
1 minus
1, 4, 3, 2.
1 minus 1.
This is minus 1. All these things are to be plus together, these pairs. So this is a minus actually, plus minus 1. Then 1, 2, 3, 5.
1, 1.
Increasing, so plus 1. These digits are being summed up. The formula is that you try to find out the number of individuals who are in the same order, the number of individuals who are in the reverse order. Suppose P number of individuals in the same order and Q number of individuals are in the reverse order. So the formula for rank correlation in Kendall sense is RK, Kendall, that is P minus Q divided by NC. Where P individuals are in the same order, Q individuals are in the reverse order. Since the reverse order, there is a minus value. E minus Q divided by NC2. Maximum possible rank that can be assigned. This is also another form of correlation, but this is not much used in reality. But one can apply it if he knows it. Many people do not know this. Kendall's rank. And this is found in Gungupta Dasgupta's Fundamentals Volume 1. So P minus Q divided by NC2 will be found. Very simple. So I am giving you some concept. AKK information criterion, Bayesian, Schwartz-Bayesian criterion, TZ. Schwartz-Bayesian criterion, Hannan-Quinn criterion. When you apply simple OLS for finding the results of multiple regression, you will automatically find that these results are coming. What are these things? This is actually e to the power 2k by n RSS by n. This is the formula. E to the power 2k by n into RSS by n. log n 2k by n RSS by n. And that is n to the power k by n RSS by n. That is not much important. And why this is so? Why these are important? Often we are interested to choose between two different regressions. Which should be chosen? What is the criterion? Suppose you run two regressions and you are interested to choose between these two regressions. The criterion is that on the basis of running the regression for both cases, if the results of one regression corresponding to these values are smaller compared to some other regression, then you go for the lower values of this. If all the values corresponding to this criterion are lower for one regression, then you obviously opt for that regression. But it is important to note that in many cases, this AKK information criterion, Schwarz criterion, and Hannan-Quinn criterion not move in the same direction. That means in one regression, this AKK information criterion may have lower value. In another case, it may have lower value. But in another regression, the Schwarz-Bayesian criterion may have higher value. In another regression also, it may have higher value. But if in all the cases, the values corresponding to these three criteria are lower, then it gives you better option for choosing that. But it is not very easy to understand this. It is very difficult also to apply it. The most practical technique is to consider only AKK information criterion, which is giving you most important or basic relevant results. So go on by checking this AKK information criterion.
So low and highest compared to low values.
Huh?
Low, I mean, when we say low, then
If
low, then
I am telling you, giving you one example, I am not sure whether you know. If you run the regression, ordinary regression, automatically these values come. That's why I am checking it. Suppose I take this, y, x1, x2 is simple one. Copy it. Ten observations were there. Being the data has come, process, make equation. Equation is already written here, y, x1, x2 and c. So y is regressed on x1, x2. Results have come, and you see that AKK information criterion, Schwarz criterion, Hannan-Quinn criterion. Is it visible from behind? Automatically see that these results will give you these values corresponding to this criterion. AKK information, Schwarz, Hannan-Quinn criterion. If these values, if the values of all these criterion are lower compared to another regression, fit on some other sample observations, then you opt for this one. If all these values are lower compared to the same model applied from some other observations, some other sample set of observations, they will be going for this because smaller values are most relevant. But sometimes for these two series of sample sets, it might be so that AKK information criterion is giving minimum value or lower value here, but for the other set, it is giving you higher value, or vice versa. Then just go in for Achic information criterion and check where it is giving the lower values and go in for that. So often we do not know how to interpret this. So this is the example of choosing between regressions. Automatically will go. One was telling about dummy variables. Dummy variables assume value 0 and 1. Dummy variables. Suppose you want to regress one variable on some other variables in which we have on the right hand side one variable which is sex. Sex can assume value female and male, which is not quantifiable. Okay. Suppose say earnings of a family. Is alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus q random term. This is y. Earnings of a family. Y dependent variable. This is x1 is equal to income of the family, which is most relevant. Income guides your expenditure or earnings. Sorry, this is expenditure. This is income. This is the sex of the household head. Household head may be male, household head may be female also. So this is income, this is expenditure of the family, and that may be some other parameter, some other variable. What will it? Tell me. X3, maybe some other variable relevant in this case. What can be? What it can be? Suppose you fit this 3 variable regression. On the right hand side, we have 3 variables, x1, x2, and x3. One variable is income, which has effect on the expenditure of the family. One variable is household heads, sales, and the last one is x3. Just tell me what can be the third influential variable on
Borrowing capacity.
borrowing.
Capacity. If you can borrow.
Borrowing capacity is not easily measurable. I want to have it quantifiable variable. Sex is not quantifiable. It can be assigned either 0 or 1 value. 1 to male or 1 to female, whatever it may be, and the otherwise. So 1 to male say and 0 to female. That is called dummy variable. Okay.
And then family belong to rural area or
I want to have it quantifiable variable. He is saying that the other variable may be urban area, rural area. That is also dummy variable. It is not quantifiable. Quantifiable. Just, right. Family size may be a quantifiable variable. Right. I was also thinking about it to write this. Family size may be quantifiable variable. How many family members? Maybe 5 or 10, depending on that expenditure values. So in this way, you shall have to fit this regression in some effective, explainable way. You should be able to explain it in some meaningful way. And if you want to regress this expenditure on these 3 variables by applying OLS, you shall have to check many things. What are the things? You check heteroscedasticity problem, you check multicollinearity because 3 variables are involved, x1, x2, and x3. And you also check autocorrelation. But often we do not check all these things because of our lack of knowledge. Even when I applied these things in my PhD thesis, I did not know many of these things, and I had no access to the software because I did PhD in 1997. I did not know these things, software. What is this? I did not know, computer. I had to take the help of some computer expert in my office in university, and he did some 3 variable, 2 variable regression for me. And that regression was explained by me in my thesis. And at that time, I had just not computer print, ordinary print, typewriter print. So you see that as knowledge gathers, you should be able to apply it. Before ending, I give you just one example. Y hat is equal to 2.20 plus 0.10 for x1 plus 3.48 x2 plus 0.34 x3. And we are here within bracket 3.4, 0.005, 2.2, and this is 0.15 within bracket. These are standard errors of the estimated coefficients. ESS is given to be 112.5, RSS is 19.5. Which N is given to be 64, which slope coefficients are statistically significantly different from zero. From zero at 5% level of significance. It's not very easy at this moment because what is the level of significance? Although I have defined it 5%, etc. Which slope coefficients are statistically significant, significantly different from zero at 5% level of significance. For this purpose, you have to find out the t statistic value for each of the regression coefficients. What is t? T is equal to estimated coefficient divided by standard error. We have completed this. Which slope coefficients are statistically significantly different from zero at 5% level of significance? I am not giving any more question here. That is the question, single question. Another question I can give you: what calculate the value of R square? Second question. Calculate the value of R square. What is R square? R square is equal to ESS by TSS, where TSS is equal to ESS plus RSS. This is easy one. First of all, I begin with this second one. TSS is equal to ESS plus RSS, and R square is equal to ESS by TSS. You can easily find it because ESS and RSS are given. You add it, you have TSS. TSS means total sum of squares. ESS stands for explained sum of squares. RSS stands for residual sum of squares. ESS by TSS, that is RSS. That is R square. If it is a higher value, then R square is very high, and the regression is expected to be good fit. R square. Test the significance of heat of this equation, R square. The first question. T or beta 1 hat is equal to beta 1 hat divided by standard error of beta 1 hat. What is beta 1 hat? This is beta 1 hat, this is beta 2 hat, this is beta 3 hat. What is T beta 2 hat? Beta 2 hat divided by standard error of beta 2 hat. What is T beta 3 hat? Beta 3 hat divided by standard error of beta 3 hat. These values can be computed on the basis of given data because beta 1 hat is equal to this. This is the standard error. So find this value. Beta 2 hat, T of beta 2 hat is equal to beta 2 hat by this. What is beta 2 hat? This is beta 2 hat, this is the standard error, and so on. Once you have these values, you test the significance of this at 5% level. How to find it? You check one value, just one value. I'll show you. Try to check one value. Any one value, first value say. Calculate it by applying your mobile calculator. Got it? The value? Beta 1, T beta 1 hat. Tell me. 0.0305. Is it?
0.0446.
This one, beta 1 hat. Calculate this.
So it will be 0.104. Upon standing error that it will be 3.4, right, sir?
How much do you get?
0.044.
No. T beta 1 hat. Beta 1 hat divided by standard error. What will take in the numerator? 0.104. Beta 1 hat divided by standard error. That is
0.0.
That is 3.4.
20.8. This is
20.8.
0.104. This is point. This is 0.104 divided by this. So this is 20.8. Check it.
Yes, sir.
20.8.
First one,
Okay.
I am considering this. This is alpha actually. T beta 1 hat. For this is beta 1 hat. This is alpha. Standard model. 20.8. Okay. Now you check the tables. The tables I have shown it here. And you must know that for T series, you should have to consider the degrees of freedom. Degrees of freedom is equal to n minus the number of parameters in the system. What is the number of parameters? 4. Alpha 1, beta 1, beta 2, beta 3. 4 parameters. What is n? 64. Isn't it? 64. So 64 minus 4, that is 60. So you see this table for T. The table for T. You find 60 degrees of freedom here, T. And suppose 5 degrees. This has to be checked at 5 degree of level of significance. often we have two-tail test or one-tail test. If you have two-tail test, then you divide this 5% means 0.05 into equal 2 parts. 0.05 by 2 is equal to 0.025. Usually we apply two-tail test for T series because T distribution, because T is a symmetrical distribution. And in this case, T 0.025 here and 60 is here, and you check the value here. What is the value? Corresponding to this value, T 0.025 and 60, 2. Isn't it 2.0? Is it 2.0? And your calculated value is 20.8. 20 point is greater than tabulated value at the level of degrees of freedom. Then what is your ultimate conclusion? Whether the null hypothesis should be accepted or rejected.
Rejected.
The null hypothesis is rejected. What is null hypothesis? Beta 1 hat is equal to 0. Beta 1 hat is 0, that means x1 does not have any influence on the right hand side variable. And since this is significant on the basis of t-test, we accept that beta 1 is significant and the variable x1 has good influence on the exponential. In this way, you can handle it. So you shall have to refer to these tables for applying t-test. I have given you some guidelines how to apply t-test by checking the degrees of freedom, that is n minus the number of parameters. Last 2 to 5 minutes, if I have any queries, I'll tell. Many things I have tried to cover.
So there are so many tests.
Many tests.
We have to choose test according to our objective type of data. Then just how can we select proper test for the.
Now you see that
Actually, I think it is more.
there are specified tests for each categories. For example, since I am not taking the class of testing, for mean there is testing. For mean hypothesis, you said mean is equal to something 0. Mu in population sense, mu is equal to 0, and now hypothesis mu stands for the population mean symbol. And already have this mean is not equal to 0. That is mean is not equal to 0. In that case, carry on mean test. That is x bar minus mu divided by sigma by root over n when standard error is known to you. Standard deviation is known to you. There is standard deviation test, mean test. There is difference between mean test. There is difference between standard deviation test. So I am referring you to the book by Datta. That is a good book for learning the testing of hypothesis. In this case, we are considering regression. So for regression parameters, we have different tests. That is t-tests. For finding the goodness of fit of a regression, you have the f-test for R-square. R-square is the parameter, and on that basis, we have the corresponding f-test. So in various cases, we have respective tests. If you consider the goodness of fit of a population, we have chi-square test also. We have one-way classified data. It is a non-parametric test. It is called based on frequency chi-square. So all these things are covered in first series of first volume of Gungupta Dasgupta's, all these bodies I have interacted. Dasgupta's son was my classmate in Nandopura business. Professor Gupta's son, Dasgupta, Professor Dasgupta, Bhagavad Dasgupta was principal of Durgapur Government College, where also I served some time back. And Professor Milan Gupta, Gun Gupta and Dasgupta, he served as moderator of some questions in Bardhan University. So I have really worked with all these three stalwarts in statistics. Anyway, so I conclude here, and the PowerPoint is given to Gaurav. I could not copy it. Might be some problem. He has managed it to some extent. You can get the PowerPoint from Gaurav. Thank you. The very exhaustive lecture. Thank you.
দাদা ও দাদা চাকরিটা বাজে জানুন
আপনি কোথায় আছেন?
আমি আছি আপনার কলিগ যেখানে ছিল
কে?
বৃন্দা
ও দিলদা। তাহলে কোন জায়গায়?
বেললাঙ্গা
বেলনা কলেজে আছে। প্রথম স্টার্ট করেছিল ওখানে।
হ্যাঁ
প্রথম স্টার্ট করেছিল সার্ভিস।
হ্যাঁ অনেক দিন ছিল ওখানে
দিনদা আমার কলিগ আমার, কিন্তু আমার স্টুডেন্ট ও।
ও আপনার স্টুডেন্ট
এমএতে পড়েছি।
হ্যাঁ
এমএতে পড়েছি। এমএতে।
ওকে এনে বর্ধমান থেকে পড়ছেন ও আমাদের কমার্সে তো অনেকটা জানি আচ্ছা পরিচিত বা পরিচিত আছে
হ্যাঁ মানে
কিন্তু আমাদের
ঠিক আছে।
হ্যাঁ কোথায় গাড়ি? আচ্ছা ঠিক আছে।